Well, hello Gophers, and welcome to the talk on Go Make Something Real. We've all been fortunate so far in the conference to see some of our incredible colleagues talk about new features coming out in Go, about open source projects, interesting use cases of the language, but I think we're going to show you something pretty unique in this talk that nobody else has been able to address yet, because at Fathom 5 we built our company around this idea of industrial applications of Go, and we're ready after our first 3 years to share out with the community what we're doing and invite all of you to join us. Before we start though, I just wanted to say thank you to my team. It has been the personal privilege of my entire professional career to lead the team at Fathom 5, and what we're doing here couldn't have been done without our chief engineer, Dr. Dave Burke, one of our lead Go developers, Stephen Maisley, and the entire team of Gophers we have cranking away to secure the digital future every day. Well, let's jump into it. We're going to talk about going and making something real. What does that mean? First of all, I'm not going to be talking about building out a data center with thousands of servers running Go at lightning quick speeds and handling millions of transactions. That's pretty cool, right? We wouldn't be at this conference if we didn't all think that was neat. But what we're going to be talking about today is running code in big machines that spin, lift, pump, heat, and traverse with incredible speed, momentum, and sharp tools. We're talking about code that is mission critical in the operation of heavy metal systems that go through rigorous pre-production and safety and reliability testing before it ever is promoted into production. And just for a little bit of fun at the beginning, I thought I'd show a quick video to indicate to all of you what we mean that's probably different than what that means at your company when we talk about high reliability testing. So let's get the quick video, set the stage for what we mean by industrial applications of Go, and we'll be right back to the talk. I hope that was kind of fun. Inside the tent you saw underneath the explosion, that was a fire pump. On a ship you would have probably 3 to 5 of those fire pumps providing the water that you would use to fight a fire with. And you can only imagine if you were on that ship or a cruise ship and there were a fire, that those pumps would be 100% reliable under any conditions, including the shock that you saw in that explosion that might be caused by a collision. And it was also kind of cool that I might be the only speaker at GopherCon that got to show an explosions video on a talk about a software language. But the key takeaway I need you to grab is that in order to get to that level of reliability, there have been decades of iteration on resolving small bugs till you get to the point where a system can literally be blown up and you still have a high reliability that it's still going to work. The price of those decades of iteration means that the software update cycle in those systems is also measured in years, not weeks. So now fast forward to things where we want that software update cycle, the product life cycle for those things to iterate in days, maybe weeks at the most. Let me give you some examples. Imagine a world where we were able to completely turn the industrial capacity of the world to making COVID masks, ventilators, PPE, and ultimately to produce vaccines, not in the millions, but in the billions, so that the entire world has an equitable opportunity to come out of this pandemic together. Right now, that can't be done because the industrial systems that produce those sorts of critical items to all of humanity can't be reprogrammed. There is no DevOps pipeline that leads to them where you can get the level of reliability you need at the speed that we expect. So what we want you to imagine is, what would it take to get to a world where you could add an app to your factory, add a product to your factory, add a new capability to your electrical plant, so that when a new optimization for burning fuel came out, you could just upload the generators and reduce greenhouse gas emissions. There are so many applications where reprogramming the industrial world will generate more food, generate responses to disease, allow us to accelerate the introduction of electrical power and smart grids and energy saving opportunities. So today we're going to talk about what we call DevOps to the edge. DevOps to the edge is this idea that we can take everything we learned from development operations and DevSecOps in the application world and apply it to creating a pipeline to deliver these mission critical applications in industrial environments. And we're at the very beginning of it, and Go is at the heart of that revolution. So we've laid out the vision. Now let's talk about some specific examples where we can implement that vision. One of the images you see on this slide is an industrial robot. A colleague of ours here in Austin, Texas is building a COVID-19 testing robot that can scale the manual lab tests from a couple tests an hour to this Friday. They should be running 100 tests an hour in the test facility, and eventually within the next 60 to 90 days, up to 400 tests an hour on one robot, and you can put 3 of these robot systems in one shipping container. This changes the game for the ability to do testing at scale. But in order to do that, you've got to reprogram the robot as we learn how to run a more effective test, and about when we move from one test that can scale to 100 to another at 400. Obviously a need to be able to deploy industrial upgrades in real time for an urgent need. On the other slide, you see International Maritime Organization 2020. What IMO 2020 does is it reduces sulfur emissions by large ships traversing the oceans by 7 times. But in order to implement that, you have to reprogram all the electrical engine control units that manage these monstrous diesel engines that power ships. Again, saving the environment requires reprogramming industrial machines. So let's think about how you might build a DevOps pipeline to do that. If you think about the fundamental technology that has enabled DevOps in the current environment, a lot of which is written in Go, Docker, Kubernetes, so much and so many other wonderful things, there's an assumption that it's probably going to be running in the cloud or going to be running in cloud Proxy on an iPhone, on a smartphone, right? There's a hardware abstraction layer that allows you to run those containers because you have a pretty solid assumption that the hardware layer is going to be configurable through virtualization, and then you're going to run a container infrastructure on top of that. Well, that works for that domain, but if we want to apply DevOps to an industrial environment, on this slide you see what we're talking about. That is a 4-story engineering test bed of the internal engineering plant of a ship. There's no hardware abstraction there. So you've got to figure out how you're going to run a DevOps pipeline from a cloud where you can adopt everything we know how to do in collaboration with remote development, cloud-based tests, service level testing of our containers and our Kubernetes clusters, and then figure out how to deploy that on the native hardware that exists. In order to do that, there's really 3 tools we're going to talk about today. There's others, but these are the 3 that I think are showing the most promise for delivering this Industry 4.0 revolution. Okay, so now we're going to jump in and talk about 3 tools that we've built in Go that I think many of you will find very interesting about solving this very complex DevOps to the edge problem. The first is that we don't get to start with new factories where we connect everything with Ethernet and use all of the existing communications, proxies, and technologies that we understand. We've got to make this work to go back to old plants and upgrade them so that they're more environmentally friendly, so that plants that already make something that's vital can do it better, faster, and more adaptable. So you have to integrate with some industrial controls protocols, like one called Modbus, for example, that we're going to specifically talk about today, that was specified in the 70s. It was run over first point-to-point serial on RS-232. Now it runs on a bus on RS-485, but we're talking about old byte-level serial protocols, actually bit-level serial protocols, where actually, the bits will overlap inside any given particular byte structure. So in order to do that, you have to find a way to connect serial device communications into your microservice. So we're going to talk about a serial proxy into a microservice. The next thing we're going to talk about is a simulation engine. We use Cyberphysical Testbeds because you can imagine no one's going to let you experiment with their plant as you're trying to integrate new technologies, right? So a safe way to do that, I have a Cyberphysical Testbed behind me. This is a maritime cyber testbed, and so you can see lots of navigation electronics to my right. These cyber test beds allow us to have actual operational technologies like an electronic chart display information system, an autopilot, and dozens of other real maritime electronics, and actually monitor and integrate with a microservices architecture. That's the cyber physical test bed. So then the question is, how can I set up a simulation in this test bed so that it looks like it's underway, a ship at sea? We can do the same thing for factories. We can do the same thing for utilities to give them not a digital twin, but a cyber physical test bed where we can run discrete event simulation so that they can monitor the results of changing the machinery control system. And then finally, we're going to talk about a singleton design pattern. There are lots of design patterns for object-oriented programming many people are familiar with. We looked at mutexes for controlling access to a shared multi-map state, and it just wasn't a good fit for a couple of reasons we're going to talk about, and found a rather novel use of a singleton pattern accessible through a channel, and we'll talk about that a little bit too. So we're going to jump in right now and talk about that first use case of taking serial industrial communications and multiplexing them into a microservices architecture. All right, so let's talk about tool one, a serial proxy for industrial signaling. And I want to clear up a little bit about what industrial signaling is. So in that diagram on the right, you see an industrial system design that's called Modbus. Modbus was introduced in the late 70s, early 80s. It was run originally over serial lines, RS-232. And you see those devices connected to the bus. Those devices could be pressure sensors, temperature sensors, RPM sensors. That could be other microcontrollers. And then you see them fed back through a translator that converts that serial signaling into USB, and now you've got to take the end of that USB and plug it into your environment. That means it's going to come in as an operating system device. If you're in Linux, like everything we build is, it's going to be in your dev folder. And that's way different than the normal production environment for Go. Most people expect to deploy into a virtualized environment, probably in containers, and actual access to the hardware level devices is not something that they normally deal with. But this is critical because if you're running in a real industrial environment, this is the only way to get the data. So we need to proxy that data to bring old devices into our microservices architecture. We want that proxy to bring it in and make it available over TCP in a multiplexed way. We want to capture that all for logs. We want to be able to replay our logs so we have a repeatable testing environment. We want those logs to maintain the original timing of when the messages came in. And lastly, and we'll talk about this one as the last topic in this tool, but having a multi-threadable proxy allows us to remote that proxy for a really cool capture the flag game we ran at DEF CON a couple months ago. And would encourage everybody to check it out next year if you're into doing capture the flag or hacking. So how do we do this? First of all, we call this application Seymour from Little Shop of Horrors. Seymour has to get fed, so this gets fed serial data. So we call this the Seymour net server. It's implemented as a standard library I/O reader writer. So anybody who knows how to use an I/O reader writer knows how to get data off Seymour. How Seymour is constructed is actually pretty interesting. There's a mutex that guards the reading and writing off of the serial bus. There's no performance issues there because the speed of the microservices accessing it are much faster than the speeds of the serial communications they're connected to. That reconnector it gets really important, you see there. That reconnector is vital to dealing with operating system anomalies and USB device anomalies that you see as you plug in different types of serial USB protocol interpreters. Sometimes the operating system will drop the file handle and you've got to re-find it when it gets recycled by the operating system. Sometimes the connection serial parameters of the USB device are different for, let's say, a mod bus than a maritime network bus. That TCP server is exactly what you would expect. That just runs the multi-threaded TCP connections for incoming requests to subscribe to the serial data. We keep a map of clients that we protect with a mutex, and then a couple Boolean variables that govern the whether the client is able to read or write. That write piece is important because once we have this serial proxy, we can actually both read and write to the industrial control bus. That is what allows the two-directional communication between, let's say, a machine learning algorithm that's identifying a proper fuel consumption algorithm to write back to the machinery controls environment to set the throttle position on a piece of equipment that may have been built and deployed in the 70s. Why we find this so cool is because we're connecting technology of today and artificial intelligence and microservices, and it's backfittable to an industrial environment where those ideas weren't even conceivable. Kind of last slide on the serial proxy, slide 10, is something kind of cool. Once you have a multi-threadable, remotable proxy, you can let anybody in the world connect to it. And so on the Cyberphysical testbed for the ship, you'd seen behind me earlier, we were actually able to remote that onto a cloud environment. We had contestants and DEF CON from all over the world proxy into that, and they were getting live streamed the serial data off of the maritime network bus, and were able to remote into a laptop connected to that. And because of the stability of Go, they were able to actually deliver cyber attacks against the testbed to try and expose new vulnerabilities in the maritime transportation security environment. All right, Gophers, we just talked about serial proxies for industrial control systems. Now we want to talk about simulation engines on cyberphysical testbeds. Cyberphysical testbeds, like the one you see behind me right here for the maritime system we were describing, are an incredibly important component of a different DevOps pipeline. We believe in DevOps to the edge, you need to create, collaborate, and test in the cloud. Then you need to deploy into a cyber-physical testbed that includes both the electronics and the code that you eventually want to run on your factory floor. You can eliminate all sorts of potential bugs in your machinery control system and in your vessel control system by using this approach. The reason why you need a simulation engine is because you have a large number of industrial electronics in these test beds, but not all of them. And you want to simulate the industrial control system at scale. So you need a mixture of actual operational technologies and emulated operational technologies. So we're going to talk about how you create the simulation engine to drive that. All right, Gophers, let's take a look at this in detail and then take a look at some code about how you create that sort of simulation engine. Just so we've got the lay of the land here. Those two blue pumps on the far left are the blue part of the system. Those are fire pumps, just like the ones you saw in the video, with valves, machinery controllers, pressure and flow sensors. And then what you see in green are the rest of the components that you would have in a full physical system. In a cyber-physical test bed for a fire main system like this, you would have a couple of real pumps, several real sensors, and then the rest of the system to reach scale would be emulated. You need to create a discrete event simulator so that you can run full machinery control systems tests, and the programmable logic controllers, the heart of the machinery control system, can't know that some elements are emulated and some are real. It has to believe that all are real, so all communications from those emulated components have to come back over your serial proxy. So you're writing back onto the bus so that the programmable logic controller believes it's talking to real components. Let's talk about how to do this in code. We create an event runner type. It has a state. That state is paused or running or stopped. That emulator client is really important. That emulator client allows the event runner to communicate with other emulated devices that are running in their own Go routines. You see that tick duration in the struct. That's how long does each tick in simulation time represent in real time. So we can run a simulation at discrete ticks every second, but those ticks can represent 10, 20, 50 seconds, an hour in simulation time. So we can run machinery control systems tests that represent weeks of activity in only a matter of hours. Now let's look when we create a new event runner. We set the state to the run state. We initialize the emulation client, and as you see there, we set tick duration to 1 second to achieve that 1 second real time to 1 second simulation for most of our basic simulations. You notice that when we actually run the event runner, we use context so that it's cancelable, and all of the events that are in the simulation are scripted to occur at that time. Future work for us is to expand the event runner so that we can reach it from any one of the different systems of systems elements, so that we can run a massive systems of systems test that includes enough operational technologies to keep it high fidelity, but is testable at scale for a city, a massive ship, an entire factory, etc. All right, everyone, we've talked about 2 of our 3 tools. We've talked about a serial proxy for industrial systems. We've talked about how to drive a simulation engine that takes advantage of that serial proxy to scale a cyberphysical testbed to a full scale environment. And then the third thing we're going to talk about is protecting the state of the system while it's accessed by multiple microservices. Let's jump in and take a closer look at that, because we think we've got something interesting to share here as well. All right, everybody, let's take a look at a pretty interesting use case. In that picture on the right, you see an industrial robot, the large orange robot there, building a car. There are multiple different state maps in that image. You have the articulated position of all of the joints in the robot. You have the activity of the end effector. You have the position of the car and the jig, and you have the overall process of variable that determines where we are in the process of building that car. Because we can't define all of the accessor functions you might need to get to that state for various reasons, it was very challenging to define mutex as the normal way of protecting a variable for this application. And we're about building an awesome team with all sorts of different skills and people on it. And one of the challenges we realize is that as we get Go developers in, they may understand how to use the mutex very, very well. But on the other hand, when we get embedded systems developers and industrial programmers in, and we're teaching them Go, it was easy to create a very clear abstraction to get access to that multiple map state. And now we're going to take a look at the code to do that. So for this one, we're just going to have a pump state that represents something like the fire pump we showed you in the explosion shock test video. And to keep it simple, there are only 3 maps of state. In that robot, you would probably have dozens. Then we're going to create a singleton keeper variable that returns a channel of pump state. And when we initialize this program, we're going to make the singleton keeper a buffered channel of 1, and then put our initial pump state into the channel, so that when we pull on the channel, we get access to it. And the way that works is through the grab function. You can grab the pump state. And in the comment there, you see how you would do that in user code. We're going to get down to that on line 36 in a minute. But what you see is when you run the grab function, you get the singleton keeper channel, and you're going to pull on that as part of the idiom we use on our team to get access to it. And then you're going to have a return, where you return the item back into the singleton keeper, and then no one else can mutate it while you have it, because the channel has nothing in it. So we're using the buffering capability of the channel to say that if it's in the channel, you can modify it and then return it. But if it's not in the channel, then you're in a blocking hold until someone puts it back, and in effect, you've gotten that protected behavior from the system. When you look in the example code there, we're going to declare the variable x, which is going to pull on the grab. Therefore, x is going to get the device status and be able to show it. We're going to be able to print it and then return it. When y grabs, it's going to get it as well because we put it back in the channel. But on line 43, when we try and print what is an x, x is 0 because it no longer has the pointer to the singleton. So we've been able to implement multiple maps protected by one construct that's easy for us to onboard new members to the team. And we think the singleton design pattern might be useful in lots of other contexts besides just our industrial automation programming. Gophers, there's a lot more depth I'd like to go into on those three topics. Happy to talk with anybody about it. But as I wrap up here, I just want to reiterate that we are a community and we are grateful for the people in our community. So on this slide, we want to list the packages that we use for various functions. We couldn't do what we do without these folks who do what they do. And we're, as a young company, still working through what we can do in an industrial environment and open source, because we're looking for ways to give back. And next year, I'm looking forward to coming back and making an announcement to the community about what we're going to do to get some of this out into the open source. If you want to help build that vision, then reach out. We've got an amazing team. We're doing things at the cutting edge of what's possible in Go in environments that nobody else has tried to develop in, and we can't do it without amazing people. And I know somebody's out there who wants to go make something real. Help us work on the COVID crisis. Help us reduce greenhouse gases. Help us build factories that can build products more equitably for everybody in the world. Come have a great time. Come to Austin. So please reach out. We'd love to talk about technology, talk about the team, hear from you, and all our contact info is right here on the slide, and we're looking forward to it. Not exactly sure, but we're going to set up a virtual meet after this talk is over, and so you can kind of pop your head in there or use the social or the email here. Thank you very much, and hopefully next year we will be all together again, and we're Fathom 5, looking forward to securing the digital future with you and the rest of the community.